All right, everyone, before we start, I'd like you to just take a quick look at our website. For those of you who have done this test and would like a little bit more information, a little bit more help with this beyond what we're doing here today, then you take a look at our website and you can download the solutions manual. I have one copy here. Not enough copies to give everyone because of the sheer amount of photocopying that we have. But it's going to look something like this. Basically, the entire exam that you've already done that I photocopied for you with handwritten answers, handwritten solutions in there. So if you go to my website, go down here on the right-hand side, Physics 30 Mock Exam and Solutions, click on that. You can get another copy of the mock exam if you really want to. Really want to try it again without any marks on it. If you want a copy of the solutions manual, just click on that, open it up. It says it might be suspicious. But you can trust me, whatever. You can trust me. Open it up. And again, it's going to look a lot like what you've already done, except that it's going to have some solutions in here as well. So my handwritten stuff, on what to do for each of the questions. We'll go through all that stuff today. But if you need something to go back to, then that's a good opportunity to do that. It's 30 pages, so I didn't want to make 50 copies of another 30 pages beyond what I already did for you guys. All right, I'm going to get rid of that. And now we'll get into actually doing the test itself. Let's start on page 1, question number 1. Let's go backwards. No, let's start at question number 1. Generally, the way that a test should be set up for the most part is that we should start off with a question that is attainable by just about everybody. Most tests are designed to be that way. Sometimes the questions at the end are a little bit more challenging, and sometimes the questions in the middle are a little bit more challenging. But we do probably want to start at the beginning because they're set up to give you psychologically a little bit of confidence. So, we joke about let's go in reverse. We don't want to do that. We do want to go in the order that they're given. Having said that, if we encounter a question that's really giving us trouble, what do we do with that? We skip it. We don't waste a lot of time on that, right? Even if question number 1 is giving us a lot of trouble, don't spend any more than a minute or so on it, okay? In the end, you have, in this exam, on average, including the time that you're going to check it over, 3 minutes per question. You can't average more than 3 minutes per question. If you do, you won't finish. So, if it's taking you more than 1 minute, say on the first question, to really know what you're doing, then skip it. Move on to the next question. Now, if it's taking you a minute and a half or 2 minutes to actually get the answer, that's okay. If it's taking you more than a minute to figure out what to do with it, then that's not okay. Skip it, move on to the next question. Put a little star by it and come back to it. Okay, does that make sense? Hey, this first question shouldn't take us any more than a minute to come up with what we're going to do for this. First question says, the risk of a motorist being fatally injured in a vehicle collision is reduced when the airbag or a seatbelt is used because the airbag or seatbelt does what to the change of momentum by doing what to the stopping force that the motorist experiences? This is a question that we will almost certainly see in one form or another. It may be an airbag, it may be a seatbelt, it may be cushioning a baseball with your glove, it may be catching a basketball as opposed to doing this, but catching a basketball by kind of cushioning it. It may be, why does the goalie wear goalie pads? In the end, you're probably going to see a question that's related to this. Okay? And the answer is, ultimately, when you're stopping an object, the impulse doesn't change. Doesn't matter how you stop the object. What does change? Well, the time and the force. If you increase the stopping time, what does that do to the force? Decreases the force. So what does the airbag or the seatbelt do? Doesn't change the momentum, or the impulse, I should say. It increases, it decreases, I should say, the stopping force by increasing the stopping time. So the answer for this one would be A. Question number 2. Even before we get to that question, we see this graph here on page 2. Remember I told you early on this year, there's 3 words that you've got to think of when you see this graph. Every single time. Okay, whether it's a really straightforward question where you simply have to do one little thing, or whether you have to do quite a bit more to it. It doesn't matter. You start off by thinking the same 3 words. What are those 3 words? Area equals impulse. Yes, area equals impulse. Okay, so you know what? You see this graph? Write that down. Write down area equals impulse. And then read the question. See what the question says. It doesn't matter what the question is. We're still going to do area equals impulse. It's just a matter of what exactly we're going to do beyond that. Question 2 says, the speed of the toy car at the end of the 1 second time interval is what? And question number 3 that goes along with that says the magnitude of the impulse of the toy car during the 1.5 second time interval is what? Well, we got to be careful here in question number 2. It says the speed of the toy car at the end of 1 second time interval. Well, the 1 second time interval isn't the entire graph, right? It's only over to here. If we want to find the speed of the toy car at the end of the 1 second time interval, then we're going to find the area of the graph, because we always do, up to 1 second. The area there is going to be base times height. So it's going to be, what do we got here? A base of 1.0. We got a height of 8. That gives me an area or an impulse of 8.0. So the impulse is 8.0. What are we going to do with it if we want to find the change in velocity? We know that the impulse is also equal to m times delta v. So we've got the impulse, we've got the mass, let's find the change in velocity. And assuming it started at rest, then the final velocity would be, oh, did it not start at rest? Oh, isn't that mean? Isn't that mean? When we solve for this, we're going to get the change in velocity, which if you're not careful, I'm sure that answer is there. Okay, they tell me in the question that the initial velocity is 3 meters per second. So if the initial is 3 meters per second and the change is, what is the change here? 1.6, then the final velocity would be 4.6. Does that make sense? That's really, really dirty. Listen, I wasn't very careful when I was going through this information here. You see that, circle it or underline it or highlight it or something, because that's clearly something that you could easily forget later on, which is exactly what I did. So the answer is 4.6. Now question 3 says the magnitude of the impulse of the toy car during the 1.5 second time interval. We're going to use the entire graph for this. Funny enough, question 3 is actually easier, I think, than question number 2, because we don't have to do anything with the mass there. Question 3, all we're going to say is area is equal to impulse, but the one trick with this one is that we've got to find two areas, area 1 and area 2. Area 1 is going to be base times height. Area 2 is going to be 1/2 base times height because it's a triangle. So for the first one, we get 8. For the second one, we get 2. We add those up, and we end up getting a total area of 10 newton seconds or a total impulse of 10 newton seconds. Who's 3 for 3 so far? Good. 100%. Let's stop right there for a couple of you. This is where it starts getting a little bit tougher. Page 4. Notice it says on page 4, use the following information to answer the next 7 questions. I've seen a scenario before where it's use the following information to answer the next 14 questions. Most times it doesn't get quite that much, but it can. Here's what I usually do when I see something that's, use the next 4, 5, 6, 7 questions, when it's more than use the following information to answer the next 2 questions, let's say. Let's circle the next 7 questions, especially when there's only 4 of those questions that appear on the next page. How easy is it? Our information is on page 4. This goes all the way up to page 7. How easy is it to forget that question number 9 goes with that information? I've seen that so many times where people are like, I just don't know how to do this. It doesn't seem like I have enough information. You don't, unless you go back 3 pages to the information that said use the following information to answer the next 7 questions. So circle the next 7 questions. All right, question number 4 says, in this diagram, the direction of the electric field in region Y is what? Well, let's look at region Y. Let's make this a little bit bigger so we can see it better. Where's region Y here? The direction of the electric field in region Y. Region Y is right here. Well, the only charge we have in region Y is this positive charge. The electric field is going to go which way relative to this positive anode? It's going to go away from it. So the electric field is pointing away from that positive anode, which means it's to the right. It would point toward a negative. It would point away from a positive. That's the electric field. Remember, magnetic field is completely different. Magnetic field is based on north and south poles as opposed to positive and negative charges. The answer is to the right. Number 5 says, as the xenon ions, Xe plus, move through region Y as labeled in diagram 2 on the previous page, they experience both the electric and magnetic forces. The direction of the magnetic force that they experience is what? This one always gives people trouble. Always gives people trouble. The direction of the magnetic force. Well, in region Y, which is right here, this blue region, because it's labeled region Y there. Again, region Y, can't really see it in this diagram, but you can on your photocopy. The direction of the magnetic field is upward. If we've got an upward magnetic field and we've got a positive particle, which way is the magnetic force going to be? Well, if it's a positive particle, it's going to be moving to the right as a result of the electric field, right? It's going to be repelled by that positive anode. So this particle is moving to the right. If we have a positive particle that's moving to the right through a magnetic field that's toward the top of the page, what are we going to do? Right-hand rule for deflection, thumb in the direction of the particle, fingers in the direction of the magnetic field, so palm is going to point out of the page. This is a tough question. Okay, first of all, because people get this, for whatever reason here, people get this mixed up with region Y. They say, well, it's upwards here and it's downwards here. Which one do we use? Well, the bottom one is labeled region Y, so we use the one that's on the bottom. It's pointing upwards. The second challenging part of this question, I can see why you're challenged by this one for sure. In order to figure out what the direction of the magnetic force is, we need to know which way the positive particle is moving. We need to know that it's moving to the right. How do we know it's moving to the right? Because it's repelled by the positive charges. That make sense? The answer is B, of course. Question number 6, also going with this information, says the xenon ions Xe plus enter the thrust chamber at a negligible speed. The minimum distance between the anode and the virtual cathode that's required to produce the exit speed is what? As soon as I see this, I think, what concept? Charged particles speeding up? Conservation of energy. We almost always do conservation of energy when a charged particle speeds up. Let's get some data down here. We want to do conservation of energy. We're going to say EI is equal to EF. If it starts at a negligible speed, that's like a car at the top of a hill not moving. What kind of energy does the car have at the top of the hill when it's not moving? Potential. But it's not MGH in this case, it's QV in this case. At the bottom of the hill, the car would have kinetic energy, 1/2 mvf squared. Now, we want to find, what are we looking for here? The minimum distance. Distance doesn't even appear in there anymore. That's okay. Okay, don't sweat that. Okay, we know that conservation of energy applies. If you can find some other way to do this question and get it a little bit quicker than the way that I'm doing it, then by all means, go ahead. But if you can't, try something that you know is valid. Conservation of energy is valid here. Worst case scenario is you end up not getting an answer from it because it's just not helpful. Okay, but it's not going to get you the wrong answer because it's a valid concept. Let's try this. Okay, we've got Q, we've got M, we've got speed. We can solve for big V, which is the potential difference. It comes out to be 153.98 volts. It's not what we're looking for. It's not what we're looking for. So what do? Well, let's try the equation now. E is equal to delta V over delta D. This E is what? Energy or electric field? Electric field. We've got delta V. We just found it. Right? The potential difference we've just found. We're looking for the distance between the anode and the cathode. We've got the electric field strength given to us. 1.0 times 10 to the 4 given to us in the data right here. So we've got delta V and we've got E, and we solve for delta E. So it wasn't just conservation of energy in this question. We had to go a little bit beyond that. But certainly when we did, we were able to get the answer there, right? We know that we started with conservation of energy because it's almost always what we're going to use, and it is always valid. Numeric response number 1, still going with this information, says, while in the thrust chamber, a xenon ion experiences an impulse expressed in scientific notation of A decimal B times 10 to the negative CD. The values of A, B, C, and D are what? Rachel was asking me a question a few minutes ago on one of the written responses, and that written response question, you had to express it, numeric response, you had to express it in the same way, A decimal B times 10 to the CD, but it had a 10 to the negative CD. That was a question that hadn't actually appeared on a diploma exam as a numeric response question. And the reason I say that is because there was a mistake. It shouldn't have been 10 to the negative CD. When they tell you that it's 10 to the negative CD, you should expect to get a negative exponent. In that question, it wasn't, because that hadn't appeared on a diploma exam, hadn't been proofread by enough people to see that there was a mistake there. I guarantee you, if on the diploma exam it says 10 to the negative CD, and you get a positive exponent, you're wrong. So you should get a negative exponent for this. This one has been field tested, so this one we know is going to be a negative exponent. Well, impulse is equal to F times delta V, but it's also equal to, F times, not delta V, F times T, and it's equal to M times delta V. Since we have the value of M, and do we know the value of delta V? I think we do. Yeah, it starts at rest. It says the speed initially is negligible. Question number 6. And it tells us the exit speed is 1.5 times 10 to the 4 down here. We know that delta V is therefore 1.5 times 10 to the 4. We're looking for the impulse. We're simply going to multiply M times the change in velocity. So let's look at that series of 4 questions that we've just done, 4, 5, 6 in numeric response number 1. When we read this information, it looks kind of brutal, right? It looks really challenging. This thrust chamber and the engine of a satellite, and man, xenon ions and electric fields and magnetic fields and whatever. With the exception of multiple choice question number 5, which I think was a real challenge question. The other 3 questions I don't think are that bad. Question 4, 6, and numeric response number 1, I think are relatively straightforward questions. Look, if we get a scenario that looks really challenging, and we can get 3/4 of the questions on a challenging scenario, we're okay. Right? We can afford to get one wrong. Now, we want to ideally get more than 3/4 of all the questions right, but on the challenging scenarios, if we can get 3/4 of them right, we're okay. Because then every once in a while, you're going to get the easy scenarios where you're just going to get them right. We end up getting a good mark when averaged together. Unfortunately, question number 7 seems to give people a little bit more challenge again. Yep. Okay. Yep. Yeah, I think I know what you mean there, Lane, okay? Let me just write down the answer to this one, and then we'll express it in a couple of different ways, okay? We get 3.285 times 10 to the minus 21. That's my answer. It's not rounded properly, but it's my answer. Now, the way they want it expressed as a 2-digit answer, A decimal B, times 10 to the, and then they want the exponent as well. So what do we got here? Well, this has got to round up, so it's 3.3 times 10 to the negative 21. Therefore, I'd express it as 3, 3, 2, 1. Does that make sense? Okay, now, if they changed it, they didn't want it expressed as A decimal B times 10 to the negative CD, but rather they asked you to express it as, let's say, B times 10 to the negative W, and they asked you to express it as a 3-digit answer, then we wouldn't put the W. They're only looking for the value of B. As a 3-digit answer, that would have been 3.29. No, that's a good question. Would it matter if our exponent was 1 or 2 digits? If it says 10 to the negative w, it could be a 15-digit answer. Or, sorry, not a 15-digit answer, but a 15-digit exponent. Okay? 10 to the negative w just means that w is a negative value, however many digits it is. Even b. A b isn't necessarily a 3-digit answer or a 2-digit answer. It could be a 50-digit answer. Now, you're going to express it as a 2 or a 3-digit answer. Okay, but just the same as when I do, let's say 2x is equal to 3. What's x equal? 3 over 2, which is 1.5. X can be a decimal number there, right? If I said 2x is equal to 2, then we'd say x is equal to 1. It can be a 1-digit answer. It can be a 2-digit answer. It can be whatever. So b and w can be whatever. W, you're not recording, so don't worry about that. B, you are recording, so read below where it says how many digits to round it to. And they'll say round to 2 digits or 3 digits or whatever. But in a case like that where you're solving for b, put in the decimal point. It's 3.29. When it's a decimal b times 10 to the cd, you're just putting in a, b, c, and d. So you drop the decimal point in that spot. Okay? All right, question number 7 says xenon ions. Here, let me get a little more space to write for this one. A xenon ion's M ion reach the virtual cathode with a speed of v1. When a xenon ion collides with a stationary electron Me in the virtual cathode, the xenon atom formed has a speed of v2. What's the relationship between v2 and v1? I don't like the notation that they use in this question. Otherwise, it's not so bad. To me, if we're going to call the mass of the ion M ion, then we should call the speed of the ion V ion. If we're going to call the speed V1, then let's call the mass M1. They're kind of switching notations, which I think kind of leads to a bit of confusion. But in the end, we can work with that. This is a collision. It is a collision, so for a collision, we're going to say Pi is equal to Pf. It's a collision in which we have an ion, a xenon ion, striking a stationary electron. The mass of the ion times the velocity of the ion, which they call, in the question, v1, plus the momentum of the electron, which is 0 because it's stationary, equals the mass of the atom, because now the ion and the electron are forming an atom. They're kind of sticking together, forming one thing. It's the mass of the atom times the final velocity of the atom, which they call v2. Again, I wish we were using consistent notation here. M1 V1, M2 V2, or M ion V ion, and so on. But that's not what they do, so we have to go with what they have. Now we want to rearrange this to solve for V2. This just disappears, right? So V2 ends up being equal to M ion times V1 over M atom. Which of them match up with that? Well, C says M over M times V1. This says M times V over M. Is there a difference there? No. So the answer is C. We didn't need to use that information, right, on the previous page, all of that stuff. But understand that it's there if we need to. The next two questions, question 8 and 9, also go with that information. Although I believe, if I remember correctly, we're not going to have to use it for that question either, for these questions either. Question 8 says the length of time in hours of this type of ion propulsion engine must be in operation in order to increase the speed is what? Soon as I see this, I start thinking what? Length of time, force. Force and time in the same question? What do you think? Impulse, right? There's certain things that just tell us what to do. You see an F versus T graph, area equals impulse. You see force and time in the same word problem, just think impulse. So we're going to say delta P is equal to F times delta T is equal to M times delta V. We're solving for time here. Yeah, we're solving for time. We've got the force. We've got the mass. And we've got the change in velocity. It's 12 meters per second. So all we're going to do here is say delta t ends up being equal to m times delta v over f. Do the math. Now, when we do the math there, we're going to get 150,000, or 1.50 times 10 to the 5. 1.50 times 10 to the 5. You got to be so careful here. What are the units for that? Seconds. Is that there? No, you see 1.50 times 10 to the 5 hours. I guarantee you, there's 6 of you in the room right now, I guarantee you at least one of you, or maybe even 2 of you, would put D as an answer there. If we can avoid that, let's think about that. Okay? If a third of you are going to put D as an answer simply because you're not reading carefully, and we can avoid that, look at the difference that's going to make, right? If we encounter 3 questions that are almost tricks like this, then that means that on average, each of you is going to get an extra point on this exam out of 50, which is 2%. So if we can avoid these silly mistakes, inevitably, you will all do better, every single one of you. Okay? I'm telling you, last semester we had someone get 100 on this exam. There's always a little bit of luck involved when you get 100, because, not that, you get lucky with guessing a question, but you get a little bit lucky with the questions that are asked, right? It's just questions that you know. There's a question out there that the kid that got 100 last year didn't know the answer to. He just got lucky enough that that wasn't the question that was asked. Right? There's always a little bit of luck involved. But I'm telling you, the difference usually between, say, 100 and a 96 or a 97, a little bit of luck, and avoiding those silly mistakes just like that. In the end, the people that get 96 and the people that get 100 are both incredibly smart. The difference is luck and silly mistakes. Number 9, the number of xenon atoms. The number of xenon atoms. Don't even know what they're asking, the rest of it. The number of xenon atoms. It's going to be total something divided by the something for 1, right? Now, this is the one that's a little bit more challenging, actually. This one, we're going to go the total momentum divided by the momentum for 1. Well, how are we going to get the total momentum for the xenon atoms? We're going to go momentum here. No, let's not do that, actually. What are we given above? The mass of one xenon atom. What if we get the total mass of all the xenon atoms, and then we divide it by the mass of one xenon atom? That'll give us the number, right? In the end, whatever you can make work, if you can go total charge, total mass, total momentum, total energy, whatever you can make work, go ahead and do it. Okay, I'm going to go total mass. But to get the total mass, I'm going to do the law of conservation of momentum. I'm going to say Pi is equal to Pf. I'm going to say the total initial momentum before anything happens is 0. That's equal to the mass of the xenon times the velocity of the xenon after the explosion has taken place, plus the mass of the satellite, which is 2,500 kilograms, times the final velocity of the satellite, which is -1. Solve for the mass of the xenon here, and it ends up being 0.16667 kilograms. The total mass of the xenon released as propellant, or as exhaust, is 0.16667 kilograms. The number of atoms is now going to be the total mass of all the xenon released divided by the mass of one xenon, 2.19 times 10 to the negative 25. We end up getting 7.6 times 10 to the 23 there. And that is the answer, 7.6 times 10 to the 23. Is that good? Now, they don't give me any real tricks in question number 9. Sometimes what they'll do for the options is give you an option that says, like, 1.6 times 10 to the negative 22. How do you know that's wrong? 10 to the negative 22 is a fraction, right? 0.00000 whatever. Can you have a fraction of an atom? No. So you know that that has to be a wrong answer. Again, they don't give me that option here, but they often do. So that allows you to eliminate possibilities sometimes if you're not sure exactly what to do. If you got to guess, let's eliminate possibilities. Now, say, unfortunately, in this question, there's not really a lot I can do to eliminate possibilities. Okay. Let's flip the page to the next question, which, surprise, surprise, goes with more reading, goes with more information. So what do we have going on here? It looks like we've got this thread that's got a graphite-coated sphere hanging from it, and this graphite-coated sphere looks to be being pulled toward a positively charged plate and a negatively charged plate. What else have we got? We got some information. We got the distance between the plates. We've got a potential difference between the plates. Delta V, delta big V, not delta little v. And we've got a force that acts on them. Looks like that's it. Number 10 says, one way to give the graphite-coated sphere a negative charge is to touch it with a blank charged rod. The process is called charging by. Here's a question we got to get, right? How do you give something that's neutral a negative charge? Touch it with something that is negative and neutral balance out to be negative and negative, right? If it's 0 and negative 10, then they're going to balance out to be negative 5 and negative 5. So it's a negatively charged rod. This process is called charging by conduction. Right? More specifically, we'd be charging by contact, but they don't ask us to get that specific here. 2, the charge on the graphite-coated sphere expressed in scientific notation is what? Well, question number 2, or numeric response number 2, what do we do for this? Any ideas? Anybody come up with any ideas to find a charge here? The only data we have is force, distance between the plates, and the potential difference between the plates. So what are we going to do here? Okay. Rachel says find the electric field between the plates. So delta V over delta D. Now, do we know right away this is going to take us to the right answer? No, we don't. Do we know right away that we have a valid concept here? Yes, we do. So if there's 5 of you that didn't give me an answer to that question that I just asked, 1 of you did. The one person that gave me an answer to that question, where do I start here, said E is equal to delta V over delta D. Okay, if that's the only thing you can come up with, it doesn't matter if it's the right thing. What matters is that it's a valid concept. Okay, we're trying a valid concept here. Worst case scenario, we end up solving for a couple things, and then we have to try something else. Okay, that's the worst case scenario. Best case scenario, it leads us to an answer. E ends up being, when I do the math here, ends up being, I didn't actually calculate that in mine, 1550. And that would be either volts per meter or newtons per coulomb, either one. All right, that's not what I'm looking for, but it does provide me with more information now. So what do you suggest that I do now? Right? Yeah, E is equal to F over Q. Remember, this is the equation that's always valid with the electric fields. The experiencer equation, as long as I have an experiencer. And I do here. I've got a graphite-coated sphere that's the experiencer. I want to find the charge. Let's just rearrange this equation. It's F over E. And I'm given the force, and I now have the electric field. So I solve for the charge here. Works out to be 5.4 times 10 to the negative 10. Now, Elaine, we go back to how they want that expressed. A decimal B times 10 to the neg CD. A, B, C, D, 5410. So we weren't sure exactly what to do to start off. Rachel came up with an idea. We weren't sure if that was going to help us, but we knew it was valid, so we went with it, and sure enough, it helps us. Usually it does. Usually when you come up with something valid, you end up solving for it. Usually it does end up helping us. Okay, but again, the worst case scenario is that it doesn't, and try something else. You're not going to get the wrong answer with it. Question 11. Question 11 says, which of the following scale diagrams is the free body diagram for the negatively charged sphere? Let's go back to that diagram again for a second, actually. The free body diagram. Well, we know that we have gravity acting down, which precludes C and D from being answers, right? Gravity has to act down on this. What else we got? Well, which way is the electric force? If it's being pulled to the right, the electric force must be to the right. So gravity down, the electric force has to act to the right. And then, of course, the string is pulling up this way. We're going to call that Ft, the force of tension in the string, which makes the answer A. '12 says use the following additional information to answer the next question. So number 12 goes with the information that's on page 9, and it goes with the information that's on page 8. So we got to be careful. If we need to use both sets of information, we will. Hey, sometimes we're only going to need to use the one set on page 9. Sometimes we're going to need to use both. The positively charged plate is replaced by the north pole of a magnet, and the negatively charged plate is replaced by the south pole of a strong magnet. The system is allowed to reach equilibrium. In other words, it's allowed to stop. It's allowed to not move. As a result of the magnetic field, the negatively charged graphite-coated sphere will do what? The key here is equilibrium. If it's allowed to stop, if it's not moving, what's going to happen to it? Well, in order to have a magnetic force on a charged particle, we need a charge. We've got that here, right? The graphite sphere is charged. We need a magnetic field. We've got that. We've got a strong north pole and a strong south pole. What do we not have if we're in equilibrium? Velocity or speed. If there's no speed, then what's the magnetic force acting on this sphere? Zero. Then what's going to happen if there's no magnetic force? It's going to hang straight down, right? So the answer is going to be hang midway between the magnetic poles, D. Don't make the question harder than it has to be. Don't say, oh, it can't be D. It's not going to hang midway. There's got to be a magnetic force. Why? Why? Something's got to be moving to have a magnetic force on it. A charged particle, that is, has to be moving to have a magnetic force, and this one's not. '13. Go figure. Use the following information to answer the next question. At least it's only one question here now. You know what? There's a real good chance we're going to see a question like this on our exam as well. They find the electric field strength midway between these charges, or to the right of the second charge, or to the left of the first charge, or whatever. We're going to draw a diagram for this. It's going to help us at least. We've got a negative charge over here. We've got a positive charge over here. We want to find the field strength right here. The field caused by the first charge is to the left. It's toward a negative. By the way, when I put the vector sign over that, I mean field, right? When I don't put the vector sign, I mean energy. Two completely different concepts. So let's be careful about putting the vector sign over it so we don't get it mixed up. The electric field caused by the second charge is which way? The electric field always points toward a negative, and it always points away from a positive. So we're going to say E2 is away from the positive. It's also to the left. You can calculate the value of both of these fields now. E1 is KQ over R squared. E2 is KQ over R squared as well. Just make sure they make R 0.25 meters, the distance from the center of it, the midpoint, to each of the charges. And then we simply add them up. We add them both up technically as negative values, but even if you make them positive, you're still going to get the right answer in this case. As long as they're the same sign, that's all. Question number 14. In all electronic camera flashes, there's a capacitor, which is a device that allows large quantities of charge to be stored. The charge accumulates and is then very quickly released. The electric energy stored in the capacitor is given by E is equal to 1/2 CV squared. So you got an equation here that you don't recognize. That's okay. If they give you the equation, you don't need to recognize it. You don't need to have ever learned it if they're giving it to you. Which of the following combinations of coulombs, joules, and or volts is equivalent to a farad? Let's rearrange the equation to solve for capacitance, which is measured in farads. Becomes 2E over V squared. The 2 doesn't have any units with it, right? So if we're calculating the value, we need to put in the 2. But if we're just finding units, we don't need to put in the 2. What are the units for energy? Energy is joules. What are the units for a potential difference? Volts. So we get joules per volt squared. Do we see that? We don't. So we have to try to come up with something else. What's a volt also equal to? Joules per coulomb. Right, so let's change that a little bit now. Let's say joules over joules per coulomb squared, which is joules over joules squared over coulombs squared. Which, if we want to divide by a fraction, we multiply by the reciprocal. Becomes joules times coulomb squared per joule squared. Joules cancels, and I'm left with coulomb squared over joules. Is that an option? Coulomb squared over joules is option A. Honestly, I don't like questions like that. You know, they're basically saying, look, here's an equation that you've never seen before. Let's play with some units that you've never seen before and see what you can come up with. It's a math skill as opposed to a physics skill. And that's not a bad skill to have, but it's not for a physics exam, I don't think. But they do it sometimes, so you got to be ready for it. Numeric response number 3. Who got this one? Anybody? Anybody get this one right? This is a good question. Good question here. Tough one though. The electron is initially at rest at a negative plate. At this point, it has 50 electron volts of kinetic energy. We want to know at any point along the path the sum of kinetic and potential energy. In other words, we want to find the total mechanical energy anywhere. Well, what do we know about the mechanical energy here versus here versus here versus here versus here? What do we know about the mechanical energy at all of those points? It's the same. It's the same. So let's find the kinetic energy at, the total kinetic and potential energy at the easiest spot. Yeah, we don't need to find it in all 5 of those spots. If you can find it here, that's great. Here, 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 it's great. Doesn't matter. Because in the end, if we find it here, it's the same answer as here and here. The easiest place to find the energy is not where the electron is. They're just trying to trick me with throwing in this 50 electron volts of kinetic energy. The easiest spot to find the total energy is here. Why? What kind of energy does it have right here? Just potential. There's no kinetic because it's not moving. It's like the car at the top of the hill. You want to find the total energy of the car? Where's the simplest place to find its energy? The top of the hill. If you know its height, right? The total energy here is just potential. So if we multiply the charge here, 1.6 times 10 to the minus 19 times the potential energy, the potential difference, which is 215 volts, that gives me an answer of 3.44 times 10 to the negative 17. The units would be joules. Now, we want an answer in electron volts, so what do I got to do? I got to convert it, right? And when I convert it, it ends up actually being 215 electron volts. Remember, 1 electron volt over 1.6 times 10 to the minus 19 equals 215 x electron volts, over 3.44 times 10 to the minus 17. That gives us our answer. "15. The path taken by an electron while inside the electric field resembles the path taken by a..." What's the shape of the path taken by a charged particle in a magnetic field? Charged particle in a magnetic field. It's going to be circular, right? If a charged particle is going through a magnetic field, just like this, the path is going to be circular. If a charged particle goes through an electric field, what's the shape of the path going to be? It's a parabola. I remember we did a couple questions like that back in our electricity unit. So, in this case, we're going through just an electric field. If it's a parabola, what's it most like? A, B, C, or D? A rock thrown horizontally from a high cliff. That's a parabola, right? It's projectile motion. In fact, if we had to solve this question, number 15, probably the best way to do it would be as a projectile motion question, which we did a couple of those again in our electricity unit. More reading. More never ends, eh? The sad thing is, if anything, as the years go on, it gets worse. So, for you guys, it may very well be worse than it was last year. But the good news is, next year it'll probably be even worse, and you guys don't have to do it. Hopefully you don't have to do it anyways, next year. So we got DNA fingerprints, we got a whole bunch of stuff in here that's probably not going to matter. Let's read the question. Okay, let's read the question. When the molecules in the biological samples are turned into ions, which are negatively charged particles, what's happening here? Well, what kind of ions are they turned into? Positive or negative ions? Let's go back and skim through our information now to see if we can find out whether they're going to be negative or positive ions. Okay? So we don't need to pay attention to all of this information. We need to pay attention to what's relevant. We've read the question. Okay, we know we need what type of ion it is. Let's go see if we can find that. Where does it tell us here? Oh, here we are. Right in the diagram, it tells us that there's little negative symbols indicating that it's negative ions, but you also see that these ions are moving away from the negative plate, which tells us that they're negative, right? So if they're negative ions, how do they become negative? Do they become negative by losing electrons? That's going to make them positive, right? Do they become negative by losing protons? That can't happen. So how do they become negative? They become negative by gaining electrons. Can't scroll this very quick, but I guess I'm on the next page anyways. Yeah, next page. They become negative by gaining electrons. 17 says, as an ion moves toward the positively charged plate, the magnitude of the force experienced is what? Here's a good question, too. It's a bit of a challenge question, not an impossible one, like sometimes we see, but it's a bit of a challenge. What happens to the force? Let's think of it in terms of gravity. That last question on page 11, the electron was going through an electric field like a rock was going through a gravitational field. As the rock falls, what happens to the gravitational force acting on that rock? Does it get bigger or smaller? Does it change? It stays the same. F is equal to m times g. What happens to the electric force as the electron goes from one plate to the other? It stays the same. Does it speed up? Sure it does. Forces make things speed up or slow down, but the force itself isn't changing. If you have a little trouble kind of visualizing that, let's take a look at an equation. We say E is equal to F over Q, the electric field experiencer equation. Rearrange that. F is equal to Q times E. What do you know about the electric field between two parallel plates? What do you know about the electric field between two plates? It's uniform, right? If it's a constant field, then what do you know about this? If this is constant and this is constant, then this has got to be constant. You want to find the magnitude of the field? Boy, oh boy, you can't mess up on this one, okay? Right in the diagram, you're given potential difference, you're given the distance, you want to find the field, you got to get this one. And this one's they ask you to express it a little bit different. A decimal BC times 10 to the D. So this time we're going to go, the answer is 2.00 times 10 to the 3. We'd express it as 2003. In forming a DNA fingerprint, a particular ion is moved 3 centimeters. The magnitude of the charge is this value. What's the work done? I'll tell you what, work to me is F times D. The electric force is going to be Q times E. Comes from my experiencer equation, E is equal to F over Q. Let's get the force. Plug it in here. Multiply it by 0.0300 meters. And we got the work. Works out to be 1.92 times 10 to the negative 17. And the answer is joules. Now, if it was me writing this question, one of my options would have been 1.92 times 10 to the negative 17 electron volts. And some of you probably would have put that in, right? Since this one's not there, let's try converting it to electron volts. When we do, we end up getting 120 electron volts, or 1.20 times 10 to the 2 electron volts. So clearly A is the answer. Next question, number 5, numeric response number 5. The electrons can produce gravitational, electric, and magnetic fields as a result of the following properties. Match the electron properties as listed above with the field that they produce as given below. You may use a number more than once. There is more than one correct answer. All right. The gravitational field is caused by what? Charge, mass, or speed? It's caused by mass. It's got to be 2. There's no other option there. It's got to be 2. A constant electric field is caused by what? Charge, mass, or speed? Charge. So it's going to be 1. A magnetic field, magnetic field is caused by what? Caused by what? Yeah, you can't have a magnetic field caused by just a charge. You can't have a magnetic field caused by a mass, period. You can't have a magnetic field caused just by speed. But when you have a charge that's moving, it causes a magnetic field. So it's going to be 2, 1, 1, 3, or what's the other option? 2, 1, 3, 1. So they're not saying, when they say there's more than one answer here, they're not saying that, you could put 2 in there, it would work. 2, 1, 2, 1, or that wouldn't work. It's got to be charge and speed. They just don't care which order you put those in. 2, 1, 1, 3, or 2, 1, 3, 1. An electromagnetic wave is created by, we got to get this one too, right? This is a gimme question. An accelerating electric charge, D. We'll take a look at number 6 here, and then we'll take a quick little break, okay? Several methods used to estimate the speed of light. Observe the time delay for an eclipse of a moon of Jupiter. Observe the time delay between uncovering a light on one mountain and having an observer on another mountain react to the sign and uncover a second light. Observe the interference pattern produced by a single source that emits light that travels slightly different but precisely measured distances. What's the least accurate? What's the most accurate? Well, let's just clarify here. Number 3 is Young's double slit experiment, right? We did that in class. Remember, we shone the laser at the 2 openings, and what do we get for the wavelength? It worked out to be really, really close to the accepted value for red light, right? So had we had the wavelength and solving for speed instead, we would have got a pretty good value for the speed of light. That's a pretty accurate method, right? What about option 2? So 3 is pretty accurate. Now, is it the most accurate? Well, let's take a look at the other ones. Option 2, observe the time delay between uncovering a light on one mountain and having an observer on another mountain react to the sign and uncover a second light. That's like Galileo's experiment, right? That wasn't very accurate, was it? Wasn't very accurate at all. How come it wasn't accurate? Sorry? Yeah, too much reaction time, too much human error because the distances are so small. Number one, observe the time delay for an eclipse of the moon of Jupiter. Well, that's another way of measuring the speed of light. Two guys, Romer and Huygens, who we didn't really talk about. That's okay. How do we know if that's going to be an accurate method or not? Well, it's going to be more accurate than Galileo's method. Why? Sorry? I think you said it, Braden. Somebody said it. More distance. Yeah, you're dealing with much bigger distances. If you're dealing with much bigger distances, then times are going to be better. Times are going to be more precise. Which one's going to be the best one? 3. Which one's going to be the worst one? So the answer is going to be 2, 1, 3 here, right? How do you fill that in? We've only got 3 boxes to fill in, right? The answer is 2, 1, 3. Where do we go? Start on the left. Always start on the left. Well, that's true. Yeah, that's true. Yeah, because there's only one kind of human error. It's one human error compared to a really big time that it takes for light, right? Versus 2 human errors over a really short time. So yeah, that's a good way to think of it. Yeah. Okay, let's take a quick break here. Okay, just get up and stretch and rest my voice for a few minutes, and then we'll move on to the last 25 questions. Okay.